Okay, great. Good evening, everyone. Welcome to our monthly seminar series in quantitative finance here at the Fields Institute. So before introducing our speaker, I'd like to thank our sponsors, Waterfront International and Scotiabank, for their continual support of this seminar series and the Center for Financial Industries. And with that, I'd like to introduce our speaker. So Steven Vanduffel is a professor of finance in insurance at the Vrije Universiteit of Brussels. His research interests vary over the fields of insurance, financial math, financial engineering. His research has been published widely in a number of journals, including Finance and Stochastics, Mathematical Finance, Journal of Mathematical Economics, Risk and Insurance, and Journal of Econometrics. He was awarded many prizes, including the Robert Muir Award, the Robert C. Witt Award, the Reddington Prize, and a few years back, when he was a teenager, the SCORE Eagry Young Economist Best Paper Award. Steven is going to tell us today all about the robust distortion risk measures. And take it away, it's all yours.
Okay. Thank you, Sebastian. Thank you for the kind introduction. Also, many thanks to Silvana for getting me here. It is really a pleasure and also an honor to be able to speak here at the Fields Institute. So my talk is about robust distortion risk measures. So this project initiated actually when Silvana, right after a PhD, came to Brussels like for 2 or 3 months. And we started this project in 2019. And now 5 years later, it is finally accepted for publication in Math Finance. Still not appeared, but well, at least we got there. So we'll use a somewhat long introduction to motivate this paper. And this motivation goes back to my earlier years, even before this, whatever award it was. So like in my previous life, like 20, 25 years ago, I used to work as a risk consultant. So long before I started an academic career, I worked as a risk consultant because from training I'm an actuary, and that's maybe the reason why. So, and I worked for a major Belgian bank. Afterwards it went bankrupt and now it's part of a French bank, BNP Paribas. And my role was there to basically to challenge models. I had a kind of free role. You know, these days, 25 years ago, these were the days that value at risk models and portfolio models, economic capital, value at risk, these were like the buzzwords at that time. And so banks were trying to build portfolio models to assess the value at risk at high confidence level, 99.97%, and so on, the risk of their portfolios. They built models, you know, correlations were all over the place, and then Gaussian copulas to aggregate the things together, and they computed value at risk numbers. And so my role was to look into these models. Were brilliant, well, not a brilliant job, but a nice job to do at least. So, and you know, you don't have to be very smart to figure out or to realize that as soon as you change a little bit the parameters and the assumptions, you know, you go from a Gaussian copula to a T copula, something like that, the numbers change, and they change drastically, right? But 25 years ago, this was like, you know, this was not so very well known. And so, you know, well, it was, kind of not rocket science, but it was kind of new at that time. And so I remember that at one point I went to the chief risk officer and I told him, yeah, you know, rather than producing these point estimates, value at risk at 99.97, you know, maybe you should produce intervals. And he looked at me and he said, Steven, that is really a great academic idea, but practically speaking, this is nonsense and very bad idea, because my job is to produce right numbers. If I produce intervals, basically I'm saying that I don't know the right number. And so I'm paid to produce the right number, so I will lose my job. And if I lose my job, then I can no longer pay your invoice. So we better shut up. You better shut up. So I shut up. Afterwards, I started a PhD. It was one of the motivations to do a PhD. During the PhD, I did different stuff. But at some point, I went back to model risk assessment. This paper is really about model risk assessment. So to set the scene, let's look into this kind of setup. We have a portfolio of risks, x1 to xn. And of course, you know very well, if we know the margin distributions of each of the risky components, and we know the dependence, the interaction, the copula, then of course we can compute whatever risk measure we want of the portfolio sum. In particular, we can compute the value at risk. Now, in the literature, it is often said, maybe not always true, but it's often said that the margin distributions is the easy part, and the copula is the difficult part, right? And this gives rise to the following classic problem, where we basically look into the maximum possible value for the value at risk of a portfolio sum, given that we know the margin distribution of the components, but we don't know anything about the copula. right? So this is a classic problem. If you look into the names, well, if you're a little bit familiar with the literature, well, many of these people are quite well known, Makarov, Rüschendorf. So it goes back to the 80s. So this problem in general, there is no general solution. So there are partial solutions. For example, for the case n equal 2, this has been dealt with in Makarov and Rüschendorf. So there the solution is explicit and well known. And apart from that, you need to make additional assumptions, like homogeneity assumptions. Or for example, there are also asymptotic results available. There's even an algorithm known as a rearrangement algorithm to approximate basically the upper bound, right? But in general, no solution. So theoretically already difficult. I want to make the point here that from a practical perspective, this problem is not really useful, right? Because this, obviously, this gives rise to very high bounds, very big bounds, So if you maximize the value at risk and you only know the margin distributions and the copula is basically unknown, you can expect that the bound will be very wide, right? So let me illustrate that with a simple example. We have a homogeneous portfolio, 10,000 loans. The PDs are known, default probabilities, and we know default correlation. Among all the loans, there's one single default correlation which is valid for all pairwise default correlations. And on top of that, we plot the Gaussian copula, and we basically apply the industry model, KMV, which is now called Moody's model. It's a standard industry standard. And basically, if you compute or you estimate the value at risk at the level 95%, with the industry model, you find 10. If you go a little bit, 99.5, you find a bigger number, of course. And now you compute the bounds, for example, using an algorithm. Then you find, well, the maximum value at risk is 98, and the minimum possible value at risk is 0%. You will not impress any CEO, any CRO with this number, because basically you say what he already knows, that the maximum value is between 0, well, that the true value is between 0 and 1. Everybody knows this, of course, right? So this is silly from a practical perspective. So what does it mean for the research that rather than assuming that you only know the margin distributions, you only need to include, of course, if you have some information, you need to include some information on dependence. And this can, of course, appear in many different ways. Right? So I started to work on these kind of problems, where rather than only having knowledge of the margin distributions, we also add some dependence information. There are various papers, I will not comment on all of them, but one possibility is, for example, to say that rather than know the margin distributions of the components, you also know some joint distribution between the components and some risk factor Z. Right? So then you add some dependence information among the portfolio components, of course. Another problem is basically where we say that we know the copula partially in some sense. The third problem I will discuss a little bit more is where we say we know the margin distributions and we know the variance of the sum, or at least some upper bound. Knowing the variance of the sum is basically saying that you know the average correlation. Think just about that. Right? So we add some dependence information there as well. So in that paper, with Carol Bernard and Ludger Rüschendorf, the main contribution is basically that we develop an algorithm to approximate this upper bound, right? Inspired by the so-called rearrangement algorithm that has been developed by Embrechts and his co-authors, like Pichetti. These two have developed that. So if you apply this algorithm, and we did that on examples, then we realized that what you typically find here, so this is the approximation coming from the algorithm, that basically this upper bound writes like the mean plus the standard deviation times a factor, and this right-hand side is basically the Cantelli bound. The Cantelli bound is the upper bound for the value at risk of the sum, the portfolio sum, given that you fix the mean and the variance. Right? So this is a seminal bound, this is very old, very easy to prove also. And so basically what we see here, what we observe is that if you apply the algorithm that we developed here, right, basically using the information of the margin distributions does not add a lot of value. You could just substitute, just move it away, remove the information of the margin distribution, and just use the mean of the sum, right? Because that's what we do in the what we do here. So basically, here we get rid of the information of the margin distributions and we substitute it by the mean information on the sum. And in many practical, this is of course not mathematically speaking, this is not true of course, that these problems are equivalent, that they give rise to the same solutions, but in practical examples this is often the case. So often less important, right? So that means that I became interested in looking into problems in which we have moment information and we ignore the information on the marginal distribution, because we know using information on the marginal distribution of the risky components, that makes the problem really hard. And moment-bound problems are easier, right? For example, this problem, you can prove this, for example, this upper bound is Cantelli bound with 2-3 lines only. It's not difficult, in fact.
Sorry, quick question. What do you mean by typically?
Yeah,
First point.
for example, if you have, so if you have 2 or 3 risks in the portfolio, then typically it's not valid. So as soon as you have a portfolio with enough risks and enough homogeneity, so not one risk that is dominating everything, then it works out, because basically you can construct the dependence such that the portfolio sum takes two possible values only. You can mix them, basically. And the Cantelli bound corresponds basically to the quantile function that only takes 2 values, right? So that triggered my interest in looking into moment problems, and also, generally speaking, while looking only into the value at risk, we should look into a family that is a little bit more richer, and that maybe includes the value at risk. And then we come up with what we call distortion risk measures. So what is distortion risk measure? So if you look into the first line here on the right-hand side, and you ignore the G, then you just see the expression for the expected value, right? So this is, of course, nothing new. So what is this G function doing? This G function is just distorting the survival function, and so that's why we call the right-hand side a distorted expectation or a distortion risk measure, right? And under some assumption on G, on this function G, which is the distortion function, we can write any distortion risk measure as a weighted average of quantiles, where gamma is the weighting function, right? And gamma is just the derivative of G, but in 1 minus P, right? So that's easy to show, that's all very well known. But the second representation is what we will use extensively in the rest of the talk, right? So gamma is the weighting function. What is important here is to realize that when G is concave, so when we have a concave distortion risk measure, which is basically a nice property as the next slide will show, then this gamma will be increasing, right? Because G prime is decreasing, and because we have 1 minus P, gamma will be increasing, right? And that we will use in a few minutes. All right, so why distortion risk measures? Well, this is a family that includes some nice members, including the value at risk, the tail value at risk, and the range value at risk. Everybody knows what range value at risk is? Yeah? So an average of quantiles over a certain range, right? That's the range value at risk. So the range value at risk, as a special case, has the tail value at risk and also the value at risk in a certain way. So we will get back to that at the end of the presentation as well. So these are examples of distortion risk measures. So concave distortion risk measures, they are important because they are coherent, and this is often seen as a desirable property. And more on top of that, if you want a risk measure that is coherent, low invariant, and combinaton additive, which are often seen as desired properties, you only deal with concave distortion risk measures. So this is a famous result of Kosuoka. So distortion risk measures are of interest. Now we come basically to the topic of the paper. So we want to maximize the distortion risk measure, basically with a portfolio sum. But what do we know about the portfolio sum? We don't know the distribution function, because then of course, there is nothing to maximize. But from the portfolio sum, we only know its mean, its variance, and we know that it's in the neighborhood of some reference distribution, right? And in the neighborhood, that means there's a Wasserstein ball, there's a ball around the reference distribution function, and the admissible distribution function of the portfolio sum is required to stay in the ball, right? And staying in the ball means that its distance with respect to the reference distribution F0 must be smaller than some square root of epsilon, right? Where the distance is the Wasserstein distance, right? So that's the problem we look at in the paper with Silvana and Carol. So how to solve this, right? It is, in some sense, amazingly simple. So let's dig into that. Yeah, we make some technical assumptions, but let's forget about these. So let's first observe that, because one of the technical assumptions that G is smooth enough so that we can write every distorted expectation or any distortion risk measure as, well, a weighted average of quantiles, so we can write it as an inner product, right? That's quite obvious. Now, what are we trying to do? We are trying to maximize, so our problem can be rewritten, so we have not done so much. And let's forget first the Wasserstein distance constraint. So first we're going to solve the problem where we have assumed the mean and the variance of the distribution function given and the fact that the distribution function needs to be in the Wasserstein ball around the reference distribution. Let's skip the last constraint on the Wasserstein distance, right? So we only assume knowledge of mean and variance and we want to maximize this thing, right? If you look at this, well, then it's immediately clear from the Cauchy-Schwarz inequality that this will be maximized when the quantile function of G is linear in gamma. Right? That's just the Cauchy-Schwarz inequality. Now, a financial interpretation that I like more than just going to Cauchy-Schwarz is the following. So, this inner product, you can also see it as the expectation of a product of two combinatonic random variables, one with quantile function gamma and one with quantile function of G, right? So how do you maximize the expectation of a product of two combinatonic random variables, and you know from both the mean and the variance, right? So that basically means that you are maximizing the correlation between these two variables, right? Because the correlation is just the expectation of the product minus the product of the expectations divided by the product of the standard deviation. But these are all fixed because we know the mean and the variances, right? So how do you maximize the correlation of two combinatonic random variables? Well, that's clear. You make one linear and the other, right? So the solution is this. Right? So that's obvious, and moreover, I forgot to stress that, because G is concave, gamma is increasing, and so we really have a quantile function. Otherwise, this would still be the maximum, but it would not be a quantile function, so it would give a problem. Right? So this problem is really simple to solve. Right? At least if G is concave. So now we're adding the Wasserstein distance constraint, so let's look into that. So the Wasserstein distance constraint, you can write it basically as a bunch of means and variances, which are all fixed. And then there's also an inner product appearing, right? So if you want to control the Wasserstein distance, you're basically controlling this inner product, right? So, and if you want to maximize this under the Wasserstein distance constraint, basically that means that for all lambda, you're maximizing, the solution must be such that you maximize this thing, right? Under the mean and the variance constraint. Basically, just plug in the side constraint of the objective Lagrange multiplicator. That's what we do here, right? And the question is really, well, how does the solution look for any lambda? That is trivial because we basically have already solved that. And then you need to work out what is the binding lambda, right? So let's do the two steps. The first step to solve this problem for any given lambda, well, we know that G minus 1, so the quantum function of G, that just means that this must be linear in this thing. Before, without the Wasserstein distance constraint, we did not have this term, right? Now with the Wasserstein distance constraint, this thing appears, but to solve it, we just make the quantum function of G linear in this thing, right? So that's what we do here. So we know that the optimal solution of our basic problem must be of this form. Now the question is, what is the lambda? Does lambda exist and is it unique, right? So, what would be the lambda? So, let's first take the case where lambda is 0. Let's just look at the case where lambda is taken equal to 0. Right? If we take lambda equal to 0, then basically this thing, of course, disappears. And basically we have the solution to our problem without the Wasserstein distance constraint. Right? Remember that I started with the problem without the Wasserstein distance constraint and that the solution was linear in the gamma. Right? So that's what we have here. So if lambda is 0, then basically we are talking about the quantum function of G0, and that's just the solution to the problem without the Wasserstein distance constraint. So what does that mean? That if the solution to the problem without the Wasserstein distance constraint, this quantum function, is in the Wasserstein ball, yeah, then it is also the solution to the problem with the Wasserstein distance constraint. That's obvious, right? If not, so let's assume that the solution to the problem without the Wasserstein distance constraint, so where lambda is 0, is outside the ball, well, what basically you see is that you need to increase the lambda, because by increasing lambda, you put more weight on the reference distribution, and so you come closer to the reference distribution, you will enter the ball, and as soon as you enter the ball, you stop, right? Because by increasing lambda, you come closer to the reference distribution. As soon as you hit the boundary, you stop. Why? Because if you go further, well, when you put more and more weight on this, of course, the value of the distorted expectation will go down, right? Because to have a maximum possible value for the distorted expectation, you would like to put as less weight as possible on this, right? So that gives the intuition for the following result, that the solution to our problem, when G is concave, has the following holds. Basically, there exists a unique lambda that determines the maximizing quantum function, right? And we can work it out. So in the paper, we give the explicit expression for this lambda. And we can, of course, also compute the maximum possible value, the B, right? And that has this, well, nice form if you want. And of course, if epsilon, if epsilon is such, so if the ball is big enough such that the unconstrained solution, and with unconstrained solution, I refer to the solution in which case the Wasserstein distance constraint does not play a role. So if this is in the ball, then lambda is of course 0. And then you are strictly in the ball and not necessarily on the boundary, right? So that's all this thing says, right? And I think it is quite simple to show. It's amazing, in fact, that this has not, I think, in some sense, not has been done before. So indeed, so if epsilon is big enough, right? So then we recover, so we have because we can also deal with the Wasserstein distance constraint. So if you forget basically the Wasserstein distance constraint, then we get the upper bound, which was also derived also quite recently in a paper of Lee in operations research, right? So, yeah. So he does also other things. So the paper is not only on that result, but the result without the Wasserstein distance constraint can also be found in that paper. Jonathan Lee, he's also in Canada. Yeah, he's in Canada, yeah, but I don't know which uni, yeah. So now we go for the general G. That was harder, in fact. So, but basically the same result. So the problem is if G is not concave, right? And basically sorry, I always go to the wrong button, right? The problem is that this function, when G is not concave, this thing is not necessarily increasing, right? And so the optimal solution in general cannot be this, because this is not necessarily increasing, right? So what do you need to do? Well, you only need to project this function on the set of increasing functions. That's all you have to do, and that gives a solution, right? So to show this, basically, this is the same step. First, we solve the problem for any given lambda, right? And that's easy, to solve that the solution must be of this form for any given lambda. That's really, well, once you have done it, and I think Silvana came up with the proof, it's only 3-4 lines. It really follows directly from the definition of a projection effect. Now, to show the existence and the uniqueness of a lambda, that's harder, and you need to use properties from this L2 projection, which can be found in literature. But that's basically, the solution is basically the same thing, only that you have to do a projection. Now, you have to be aware that computing this projection for any given function, for any lambda, there's in general not an explicit solution, right? You need to go to numerical procedures, and these are available in the literature, right? So there is not, in that sense, not an explicit solution. So, how long do I still have some time? Huh?
Yeah, like 20 minutes.
20 minutes, okay, ça va. So, note that I started from an admissible set in which I say the mean and the variance of the distribution function are fixed, and they are not necessarily the same as the mean and the variance of the reference distribution, right? Now, in many applications, of course, it does not make sense to assume another distribution function for G than for the reference distribution, but it could be, so at least it is more general. But yeah, so the point I want to make is that it could also be that you're interested in maximizing distortion risk measure, given that you only know that you are in the Wasserstein ball around the reference distribution, right? So how can you solve that? Well, you can solve, so basically, because of the Wasserstein ball, we know also the range of all admissible means and sigmas and standard deviations. of the distribution functions, right? They cannot take any value because then you go outside the ball, right? And so for any mean or variance, we can figure out the maximum value. So you need just to do the second step to optimize over the admissible means and variances. And then you get the solution to this problem, right? Which we did. And yeah, well, it was quite tedious, but well, we managed to do that. So one interesting case, because I said in general, it is hard to derive the solutions explicit because we have to do this projection. But for the case of range value at risk, which in industry is somewhat important, there we can do it. And the basic reason is basically that the gamma, the weighting function, is a quite simple form. So the weighting function for the range value at risk is 0, constant 0, right? So it's a simple function, right? And so there we can compute the isotonic, or the L2 projection, also called isotonic projection, explicitly. So just to give you some, yeah, so that's, sorry for that. So we could do it for the range value at risk, and then we could also do it for the case of value at risk. The value at risk was a little bit more tricky, and I think we spent quite some time in proving it, but we used the result from range value at risk, because value at risk, you can see it as a kind of limiting result of the value of the range value at risk. You know, just, yeah, you just take the alpha and the beta equal to each other. So we could guess the solution, but then to prove that it was actually also the solution, that was quite tough, I think. But we managed to do that. So we could work out explicitly the case of range value at risk and value at risk. So maybe I just plugged in the slide just to give you some idea. So let's look into the middle graph here, right? So the blue curve is basically the lambda times f0 minus 1 plus gamma, right? So we want to project this because, you know, we had this function gamma plus lambda times the quantile function f0, and that we need to project, right? So how does this projection work? Well, so the blue curve is of course not increasing, right? Because the gamma makes that this lambda times f0 minus 1 jumps at some point, right? Where the gamma takes value, the constant value. So, but in order to project, yeah, basically you need this blue function, you need to make it increasing, and it's in the cheapest possible way, so as close as possible to the blue line. So that it becomes clear, and one can also prove explicitly that you get one flat piece, right? And so we can basically work out where the flat piece is, right? So this can be done explicitly, or seen, well, it's explicit, yeah. So applications. Let's first look into the, well, the actual application, where we go back to the CRO, and he says, well, listen guys, I want to assess the model risk, or I want to assess the risk of a portfolio of non-life risks, for example, and somebody has told him that the Pareto-Clayton model is the reference model, right? But there are also a bunch of other actuaries, and each of them, they have their own favorite model, based on data or other considerations, expert information, whatever. So one actuary says, oh, it should be rather log normal, gamma, log logistic, y-bull, and the others, right? So the first three here of the alternative models, they are somewhat heavy-tailed, the others are light-tailed. Right? And also Pareto-Clayton is considered as a heavy-tailed, is a heavy-tailed, gives rise to a heavy-tailed distribution, right? And the models have in common that they all have the same mean and variances. Right, so the moments are matched. Okay, so let's now look into the assessment of the, in this case of the value at risk, the way they can deviate from the reference value, which comes from the Pareto-Clayton. So the reference value is not mentioned on the slide, but it's like 25, right? So the value at risk at 99% probability level is like 25. So if you work out the Cantelli bound, right? So you work out the maximum possible value at risk and also the minimum possible value for value at risk, given that you ignore Wasserstein distance constraints, so epsilon is equal to infinity if you want. So then you find this minimum 10 and this maximum 51, right? So now we add the Wasserstein distance constraint, and of course we need to choose the epsilon. So how did we do that in this application? For each of the alternative models, we worked out the distance with respect to the reference model. Right? We can compute that. We can compute the Wasserstein distance. If you have two distributions, you know, it's just an integral of a difference of squared, squared difference of quantile functions, right? And then we integrate. So we can compute that. We did it for all the models, and we take the maximum possible value for the epsilon, right? And then we work out the worst case distribution. So we do that, and then we find for the upper bound 41. I forgot to say that in the paper, everything we do for upper bound, we can also do for the lower bound, right? So we find now that the bounds become narrower. So we start with 1051, now we have 1541. So then we also considered the fact that, okay, let's now only take as plausible models the heavy-tailed ones. So we forget the last four, and we only take the epsilon coming from the maximum possible value for the Wasserstein distance coming from the three first alternative models. So the log normal, the gamma, and what was it, log logistic, or something like that, yeah? And then the epsilon becomes smaller, right? Because the Pareto-Clayton is a heavy-tailed model, so the distance becomes smaller. And then also, of course, the bounds improve, right? So, and they, well, you know, they improve still considerably. And then maybe one reference interval, I would say, is when you would have only the mean, the variance, but also you know unimodality, right? So that's something alternative we developed in the other paper. It's also quite nice. In that the upper bound is not so far away, right? 38 is not so far away from 35, right? So yeah. So that's one application. The second application is robust portfolio optimization. So what do we do there? So in the first version of the paper, we did not have this, but the one referee said, oh, this is cool, but not cool enough. So you should do something with robust portfolio optimization. So we had to think a little bit about what can we do. So this is what we figured out. So static setting. So you know we just want to find the best portfolio weights, right? And we can choose between different assets. You know, R1 to Rn basically, but we only know from the multivariate asset return, from the multivariate distribution, we only know the mean and the variance. The mean vector and the covariance matrix, sorry, right? Of the vector of returns R1 to Rn, right? And for each portfolio, we denote by Gx the portfolio loss, right? Which counts basically from assigning the weights to each of the assets, right? Which have return Ri. So, you know, this is the portfolio loss, and we know, of course, the mean and the variance, right? But we don't know from the portfolio loss, we only know its mean and variance, right? And we don't know the full distribution, but we assume, or we know, that it is somewhat close to a reference distribution. And the reference distribution for each portfolio X is a location scale, comes from a location scale family, so you may think that the reference distribution is basically, you just think about the normal, for example, right? Which is of this form, of course, right? So, and now you want to figure out what is the best portfolio, right? So usually if there was no ambiguity, if everything was known, then you would just take the portfolio X such that you minimize the distortion risk measure, your favorite distortion risk measure. But now we don't know the distribution function, so we are going to look for the best case under the worst possible scenario, right? And the worst possible scenario is that for each portfolio, we look at the worst case, right? And then we look for the portfolio that is the best performing under the worst case scenario. Well, so look for the worst and hope for the best, basically. So we look into this problem, right? And so this problem, without this Wasserstein distance constraint, has also been considered in the, I think, in the same paper of Lee again, right? So maybe after all he was a referee. No, maybe. Okay, I'm just kidding. Oh, this is recorded, so I should be a little bit careful. Okay, so I think the problem is clear. So how do we solve this? So the inner optimization problem. Well, using a result of Popescu, saying that we maximize over the joint distributions of R, given that we only know the mean vector and the covariance matrix, is equivalent to maximizing over the set of distributions over the set of distributions function for each portfolio, given that we know its mean and its variance, right? That's a known result, right? And then, of course, if you get rid of this GR, but you replace it basically by GX, so the loss distribution of each portfolio, right? Then we have really the problem we discussed before, right? So this inner maximization can be done, and so this just gives the bound in case where you maximize the distortion risk measure on the mean and variance constraint and the Wasserstein distance constraint, which we derived before, right? So, and then we still need to deal with this minimization, right? So, but the first step is then that we get that this problem we started with is equivalent to this minimization stays, but this inner maximization, right, it becomes now this, right? So now this looks more familiar because now we only have mean and variances, and it looks like quite simple. The figures here, these epsilons, are portfolio specific in general. We started with that, right? But it could be for some portfolios that you have a bigger epsilon, because epsilon could maybe be estimated from statistical data. For some portfolios, you are maybe further away from the reference distribution than for other portfolios, right? That makes sense. If you have a very concentrated portfolio, the epsilon should be bigger than if you have a very equal weighted portfolio, right? So, but the principle you can solve it, right, in principle. So, but explicit this is hard because this epsilon x, right, which appears here, can depend on the portfolio weights in a very complicated way, obviously, right? So let's make now an assumption where we say that the epsilon x, so the tolerance levels basically of the Wasserstein bound, the radius, let's say that is of this form, right? Now you can prove that the maximum possible value for each portfolio weight is 2 times sigma x squared, right? And it is between 0 and this maximum value. So A is between 0 and 1, right? One can, yeah, if you look a little bit, that's easy to show. And we basically say that epsilon x is of this form, where A is some constant. Maybe one can estimate from data. In the paper, we give some hints. So of course, if A is 0, that means that there is no ambiguity, there is no Wasserstein distance constraint, and then we just have a very classic kind of mean variance optimization problem, right? So there's no ambiguity. If A is big, right, then the Wasserstein distance constraints vanish basically, and we come back to the problem without the Wasserstein distance constraint and the problem that was considered in the paper of Lee, right? And then of course the interesting case, at least for our paper, is that when you are in between, right? So when the epsilons play a role, and then basically the problem writes like this, right? Now, and this problem can be solved. There are well-known techniques. I'm not an optimization guy, but those who know a little bit about optimization will realize that there are many algorithms available to solve these problems, right? So, and what you see, of course, that if you would do it, then of course here, if A is 0, then you get portfolios that are more risky, right? Of course, when A is very big, right, then you get very conservative portfolios, very conservative solutions. So conservative means that you put more weight on riskless assets or less risky assets than on risky assets. And here you go in between, right? And the third case, you can really interpolate between the first and the second case by increasing the A, right? If A is 0, you're on the first case. If A becomes bigger or big enough, then you're on the second case and you go in between. So that was my second application. So I still have 5 minutes. Yeah. So I can say something about a last application. So this is the problem where we say, okay, we look into, just think basically about the Black-Scholes market, and you say, I'm interested in payoffs that only depend on the terminal value of the underlying risky asset, as big T. And there is a pricing measure. You know, if the market is complete, just think about the Black-Scholes if you want. There's a unique pricing measure, right? And the price of any payoff that is in the set is of this form, of course, right? And we can also write it like the expectation of psi times x, where psi is the state price density, right? The Radon-Nikodym derivative, right? So, and this is, of course, this is the object or the representation of the cost we care about. So what are we going to do? In the first step, we are going to minimize for a given distribution we are going to look for the payoff in this set that has minimum cost, right? So we are not the first to do this. Actually, this is not the current Nobel Prize winner, but one of the Nobel Prize winners of 2 years ago, Phil Dybvig. He was one of the 3 who won the Nobel Prize in economics 2 years ago, I think, together with Bernanke and Diamond. So long time ago, he came up with the solution to this problem, and the solution is super simple, right? So he says that in order to minimize the cost, right, in order to figure out the payoff that for a given distribution has minimum cost, well, this payoff must be of this form, right? So on the right-hand side, psi is assumed to be continuously distributed. You have a uniform, and here you have the, you apply the quantum function. So in any case, x star has the right distribution. That's completely obvious. And it's also the cheapest possible. Why is the cheapest possible? Because it's antimonotonic with psi, right? And because of the antimonotonicity, you minimize the cost, right? Because the cost is this thing. And so since the distribution of psi and of x is given, in order to minimize this thing, you need to make x and psi antimonotonic, right? It's trivial, in fact, right? So, yeah. So that's of interest. Moreover, once you have such a payoff, let's call it a cost-efficient payoff, you can write this price of a cost-efficient payoff like this, right? It looks like a distortion risk measure representation, right? Where gamma is now the weighting function. Now gamma is not necessarily positive. It's not positive, in fact, unlike before, but that is not important, in fact, right? So the cost-efficient price can be written as the minus of this integral which we were dealing with before, right? Okay, now let's go to our problem. We consider the generalized cost efficiency problem, where we minimize the cost. So we look for the payoff that has a distribution such that the distribution is in the admissible set. So there must be mu comma sigma, obviously, right? So basically we say the payoff needs to have a certain mean, a certain variance, and it needs to be in a Wasserstein ball around the reference distribution, right? And it must be as cheap as possible, right? I think this is a useful problem. So by the way, so I think this problem of deepfake, I think this is really great. So why maximizing utility? If you're an investor, if you ask what is your utility, Vanduffel, for me it's hard to say, but if you ask me what is your favorite distribution function, how would you like the distribution of your terminal wealth be look like? I can probably give you more, I have a better idea. I can probably make a graph. Whereas a utility function is a little bit more obscure, I think. But anyhow, that's maybe a side remark. So I think this problem makes sense. So how do you solve it? Well, first, you just realize that the payoff must be cost efficient, right? Because the payoff has a distribution function. The optimal solution must have a distribution function, obviously, and it must be the cheapest possible. So, the optimal payoff must be cost efficient, right? So that means that we only need to solve this problem, right? But this is actually the problem we have solved before, right? This is actually like maximization of a distortion risk measure, given that we have constraints on the mean, the variance, and the Wasserstein distance, right? Yeah. So this is, so we can actually solve this, because once you have the maximized distribution function, then you just plug it in again in this formula, and then you have the optimal payoff, right? So maybe a little bit of advertisement to stop. So this paper that I discussed, except from the very last part and the long introduction, is a chapter. So the paper with Silvana is a chapter in this book. I think it is maybe the very last chapter for historical reasons, because we started, as I tried to explain, with problems in which we know the marginal distributions of the components, and then we built up and we realized that, oh, maybe we can also just stick to moment information. And so that's also the way the book evolved. I don't say that you have to buy it, but if you want to buy it, so yeah, of course, why not? Huh? I will not become rich of it, so, but yeah, still, why not? Yeah, and thanks a lot for your attention. Here are some relevant references. Thanks a lot.